Microsoft Research, Twitter, name an AI lab. He worked there. He's currently research team leader at Araya. And he's going to talk to us about Neuro-Inspired AI.
Yeah, well, thank you for remembering, just the course of the labs I've been in. I'm just kidding, that's most of them. So, I have to apologize, this was a bit last minute, an invitation, so I didn't have much time to prepare the slides, only about a day or so. So it's not going to be as polished as some of the other guests. I do not have a list of wonderful badges like Olaf does. But yeah, so I'm currently a research team lead at Araya, and one of the other things I do at the moment is I work as a dance teacher. So given that, thank you, given that everyone's been sitting for an hour and a half, can everyone please get up? No.
Why not?
And go.
What?
Okay. Deep breath in. And release. Okay, you can sit down. That's all. Don't worry. No. Just let everyone release the tension, wake up a little bit. Also need to wake up a little bit.
What kind of dance do you do?
Bachata is my main one. I also do salsa and kizomba. Cool. So, along the lines of all of the other talks here, we'll be talking about Neuro-Inspired AI, reinforcement learning, which everyone has moved on from, unfortunately. So, I will talk about some of the things that everyone else, all the other speakers have moved on from. A little bit about consciousness, which some people have talked about. Embodiment, which is apparently no longer needed if we have programming. So yeah, a bit unfortunate, but I'll go ahead anyways. Okay, so this is the question that I've been asking myself from the inception of trying to do research is, what is intelligence? And I guess to start with, researchers, especially working on old schools, fashions, AI, would have said, if you can beat a chess grandmaster, that's very intelligent. And then afterwards, you can be a grandmaster at Go. If you can solve mathematical theorems, so like the things that people, dedicate decades into doing, thinking very hard about these things, this is what people would have said. But, the system is intelligent, it can do these things. And then we started solving these things, and it turned out that we could, beat chess grandmasters, but we couldn't get a robot to walk properly. So simple things for humans, like walking, just seem very difficult for AI systems. And so someone called Hans Meyrbeck came up with this paradox, which is the things that we think of as the sort of pinnacle of human intelligence, actually we can get AI systems to do without much difficulty, but the things that a baby, a toddler can do, we still find very hard to get these things to work. And so if you think about the origins of AI, it was very much based on like symbolic AI and logic theorem proving and things like that. And there was a group of people who started working on what they thought of as embodied intelligence afterwards. They say, oh, actually, we need to get things working in the real world. If we can't even solve walking, what's the point of this? And then moving on from sort of these hard-coded rules in symbolic AI, of course, there's a large field of what we know as machine learning, which is can we learn from data instead of having to hard-code everything in. And in recent years, obviously the thing has been deep learning, which is flexible function approximators. So if we have these models that can really approximate a function very well, then we can throw lots of data at them, and then they can learn even if we cannot specify rules in advance. How could we even define intelligence? So in general, we try and say there must be some sort of task that we're doing. The question is, of course, how do you define a task? It's very difficult. Very tricky thing is how do we measure performance on this task as well? In machine learning, we think about things like classification accuracy, but when it comes to robotics, like it's very difficult to say, is the robot walking well, or something like this. So I think Ilya said at some point he wanted to hear what the speakers would define AGI as, so here's at least one sort of definition. So if you buy into the idea that there are tasks and there's performance, then AGI would be an artificial system that is at least as good as the average human across all the set of tasks that we think are relevant for humans. So, that could be walking and playing chess, right? We don't really have a system that can do both. So that's AGI, and then we look at some areas within AI in general. Machine learning, as I mentioned, is being able to improve at a task given data. And the thing which no one else here wants to do apparently is reinforcement learning. So this is optimal sequential decision making under uncertainty. So if you contrast this with what's usual in supervised learning or unsupervised learning, where you just get lots of data and you make an inference over that and it's static, you have an agent that is existing in an environment and it has to act in Cole's framework of causality. This would be an intervention, and it's on an ever-changing world. So it's not like you can continue seeing pictures of cats and dogs and that's never going to change. The actions you do influence the world that you inhabit, and the world is also changing whether you like it or not. And so RL is dealing with this very challenging problem, and we'd say that intelligent systems are trying to solve this RL problem. Interestingly, people have in the past even defined what they would say as theoretically optimal agents. So you make some assumptions and say this RL problem, actually you can define an agent that will solve it under these very broad conditions. So Ixie from Hutter uses Solomon induction and can solve these things using programming, etc. Theoretical. So reinforcement learning. This is the basic setting. So we have an agent that is inhabiting some sort of environment and it has a policy. So basically at every time step, remember this is sequential decision making, it observes the current state of the world, it uses its policy to decide what action to take in the world, and then when it takes an action in the world, we go to the next time step, and then it observes the next state, how the environment has transitioned, and also a reward. So we're assuming there's some function that is giving us a sort of optimality of what the agent is doing at any time point. And the sort of goal of reinforcement learning is that the agent should learn, it should update its policy based on its observations so that it can maximize the sum of rewards over time. And so reinforcement learning is quite interesting. It actually is sort of came from many different areas. So for example, it came from behavioral psychology, so Skinner doing experiments many decades ago with different animals, and also the field of optimal control, which is of course used in process engineering, robotics, all of this sort of stuff. Combine the two, and itself it still overlaps many fields. So for example, it's studied a lot in cognitive neuroscience, psychology, these sorts of things, because we're saying that basically animals, including humans, will be using reinforcement learning algorithms trying to solve reinforcement learning tasks. What I found particularly interesting is that there is not necessarily a one-size-fits-all algorithm that is going to work for everything. And animals are known to use different types of algorithms that are based on their various trade-offs. So here's a diagram, for example. So those of you who know a little bit of reinforcement learning would have come across, say, model-free and model-based algorithms. There is something that sits in the middle called successive representations. There's also something that's a little bit more esoteric called episodic control. And you can see these algorithms actually have these different trade-offs in whether, how flexible they can be, like depending on like the experience you've come across, how well they make use of data. So model free algorithms need a lot of data to work well, but episodic control doesn't. And also the inference speed, like how long does it take to make a decision? So model-based algorithms can take a long time, and model-free algorithms don't take so much time. And so if you think of the concept of bounded rationality, that intelligent decision making agents don't actually have all the time in the world, all the energy in the world to make their decisions, then they're not going to be fully optimal. They're going to have to make it with respect to some of these constraints. And for those of you, who do look at reinforcement learning, you will know that, especially in the last half a decade, a few years or so, there's been quite a lot of success combining model-free and model-based algorithms. So I think, I would say, hopefully you would see more of these cross-pollination of ideas and cross-pollination of algorithms. So I know this is maybe, even those of you who work in reinforcement learning may not have come across this. I thought I'd show some of the work that I did in this. So episodic control is a non-parametric algorithm, and at least biologically, it's sort of thought to occur thanks to the hippocampus, part of the brain, where episodic memory is thought to be. And the way that episodic control works is that you go out in the world and you do different things, do different tasks. We store these sort of like first-person experiences in episodic memory, and when we come across a similar situation again, actually what we can do is sort of like retrieve similar memories from the hippocampus, compare what we're trying to do with that, and then use our memory in order to make these decisions. So rather than sort of storing them in the, like the parameter space of your network, or like your connections between the neurons in your biological brain, actually is retrieving directly these memories. So it is much faster, more data efficient than parametric methods, but the trade-off is that it has less generalization, so you're really limited to what is close to what you've observed before. And yeah, so in the past I did some research on improving these methods based on ideas of like forgetting and memory consolidation. So moving on, this was already mentioned, so Kahneman's system 1 and system 2, so instinctive versus deliberative thinking. And the second part is thought to link to conscious processing, self-awareness. What exactly is consciousness? And Olaf did sort of mention that we have to be kind of precise when we talk about this thing, because actually it refers to many different sorts of things. It's a very mysterious thing, it's very multifaceted. And for example, when you talk about consciousness, some people might think of phenomenal experience, which is what does it feel like, or the experiential things that we have. So why does red look red? Why does ramen taste good, or something like that, right? But that's just one aspect of consciousness. Interestingly, if you think about science fiction literature, typically, if you look at the systems that are thought to be intelligent, then they usually thought or seem to have some sort of consciousness. But should this be the case? Like, should intelligent systems also be conscious? And so when I joined Araya, this is some of the work that I started doing. Previous stuff is from my PhD. So along those lines, Araya, the company I'm currently at, our CEO, he's a famous neuroscience consciousness researcher. So in this work that we were doing, basically we tried to say, okay, let's look seriously at theories of consciousness, see if we can stop making them less vague, and use some ideas and terminology, things like that from the AI research in order to make things a little bit more concrete, because if we make things concrete, then obviously we can start doing scientific things with them. So in this case, we looked at 3 theories of what we call conscious function. So this is really about functionality. Like they're about things that you can actually do to do practical things. It's very much, these are based around the ideas of attention. Attention has been mentioned before. And access consciousness, so this is the fact that you are actually consciously aware of information. So you probably heard, oh, you can have some knowledge in your subconscious, you're not really aware of it, and there are things which you're consciously aware of. So in this work, we looked at 3 theories of consciousness. So the most famous one is a workspace theory, which is an idea that consciousness is actually a sort of central area in the brain, which receives information from all of the sort of like sensory modality inputs, visual cortex, auditory cortex, processes this information. It's actually what we consider working memory, and then can broadcast this out. So all of the different modules in the brain can make use of this information. If we hear something, we can't see it, processed by our whole workspace, and then this can be used to make decision making, and we can go look for something, right? Information generation theory. This theory says that conscious information is actually not directly what we experience, but is actually something that is re-experienced or reimagined by a generative model that exists within ourselves. So it's actually not the sort of experience we get directly, but somehow it is being filtered through this generative model, and that explains some sorts of cognitive biases that we have, and some other sort of strange phenomena that you get when you do consciousness studies. And then finally, attention schema theory. So this is not attention itself, but meta-attention. It's the idea that we can actually pay attention to our own attentional processes. So I might be paying attention to, let me find someone who's on the phone, that person over there. And so I'm paying attention to them, but I am aware that I'm paying attention to them, and I can obviously move my attention elsewhere. So it's this higher level meta-attention property that attention schema theory is all about. So we sort of have this proposal of how they might fit together. And in this paper, we also use these ideas to talk about something called mental time travel, where it's this sort of apparently, as far as we know, though there's some debate, uniquely human property. Whether great apes and things can do this is still a little bit of a debate, which is the idea that we can project ourselves for the first person into the past or the future, using episodic memory and counterfactual thinking. And so some of the things we did in this paper is we tried to make this a little bit more precise, right? And so there are many different ways that people experience the world, can replay things from their memory, try and simulate stuff, world models, etc. But in this paper, we sort of say, we think about trajectory, states, actions, environment, all these things, that we say that mental time travel really is something that's just a little bit beyond what sort of AI systems are capable of. Again, maybe you could debate this, but at least what we try to do is make this sort of system formal, and ties into like these theories of consciousness that we discussed. So we're saying, maybe you can get to intelligence just by throwing lots of data into a big foundation model. But there are theories of conscious function which actually have some ideas that are potentially useful for intelligence and generalization and stuff like that. So if you go ahead and implement them, we think you would get these nice properties that we observe. And considering that deep learning models, particularly CNNs, for example, have been used actually in reverse to help study the brain, an idea that I had is that why can we not do this, the same thing for models of consciousness? Can we actually build larger scale deep learning models which implement theories of consciousness, and then sort of use them and try and map them to what we see in the brain and do these similar sorts of neuroscience studies. So this is some current work that we're doing in Araya, where we're trying to implement an agent which has some degree of consciousness according to some criteria, but actually put it in a 3D multimodal environment. It has vision and audio with realistic inputs, and really scale up these sorts of models rather than keeping them sort of mathematical curiosities. And so we're focusing on global workspace theory in particular, which is quite popular and it's quite a nice architecture to work with when it comes to intelligent agents. There was a recent sort of survey position paper by Butler et al. Where they came up with a set of what they call indicator properties of consciousness. So they looked at many popular theories of consciousness and they said, okay, well, you know, here we think are like some definitions or like properties that we can really make somewhat exact about them, and therefore, you know, if you implement them, then you would say they're fulfilling these theories of consciousness. And they sort of made the argument that actually there's probably, you know, agents that satisfy some of these, but in general, like there's no agents that satisfy all of these. And they suggested 4 properties for global workspace theory, said that to the best of knowledge, no architectures, agents implement all of that. So we came up with one that we think does that, and we are currently running experiments. So fingers crossed, the paper's currently under review and good soon. So final bit of my talk, embodiment. Do we need that, or are programs enough? Jury's out for now. So can we learn about the world just from text? Surprising amount, apparently. Can we learn about the world passively without interacting with it? Again, apparently quite a lot. But you know, even if you can, it does seem like that acting in simulation or the real world is going to at least work. So this is the sort of thing that I'm focused on. And so right now I'm quite passionate about working at robotics and machine learning and all of these things because you know, I want to do practical research that can have positive impacts on society, things like automating labor, etc. So you know, working on like sort of factory systems with AI and things like that. And just to conclude, I am a PI with the GST Moonshot project to work on brain-machine interfaces. So Moonshot project is large grant scheme happening here in Japan. So some of the research I do involves working with brain-machine interfaces, and that is actually a very true intersection of biological and artificial intelligence. So what I like about this is that, you know, in the short term, obviously this can have nice implications for healthcare, for helping people with severe disabilities, for example, and whether you're into Neuralink or Ghost in the Shell, maybe we'll have a future with widespread neural implants. And I went through a lot of things quickly, so there's a bunch of references to the work I talked about, and now happy to answer any questions.
Questions.
Yeah. How important do you think human-like consciousness is for general intelligence? I mean, because we make the assumption here that the kind of general intelligence that we know about are humans, and then therefore we assume that it has to be conscious. But is that a valid assumption? And what backs it up that it's necessary?
Right. So I wouldn't say that it's necessary or that we know that it's necessary, right? The second thing I'd say is consciousness is an overloaded term, right? Like it can actually refer to a whole bunch of things. I at least split it into 2 things, which is phenomenal consciousness, like what is, you know, feeling, and self-awareness. Like, do we have a self? Do we have an idea of like self, right? And if you have an idea of self, it's, you know, much easier to make a world model where you can causally disambiguate yourself from the things outside of you and yourself, right? obviously there can be different aspects of consciousness, etc. So I'd say, do you need to be conscious to be generally intelligent? Not necessarily, but there are certain aspects of consciousness that we think are functionally useful, right? And so if you had a system that implemented or had these systems in place, then it should help when it comes to being able to generalize and do different tasks, etc.
So it's more from a safety perspective? What features do you think are important?
Oh, so I'll go back to the one that I kind of said. I think this idea of self-awareness, or the fact that you can actually separate yourself and think about this as a distinct entity from the world around you, and then also sort of counterfactually manipulate this system, right? So you can say, I myself, this is the environment. Oh, I can change the environment, right? I can imagine what it would be to be in other situations. And I could change myself. So I could imagine myself on the moon in a spacesuit, like, and I'm going to go there, but I could do that, and prepare myself for a future where this sort of situation might happen.
Is that a good thing?
For intelligence, yeah.
Oh, okay. Aaron.
I'll follow up on that. Have you ever encountered anybody who does not have a sense of self? As in this distinction between themselves and the environment simply doesn't exist for them.
You could probably ask GPT-4 to act like that, but I haven't.
But an
I
actual
haven't come
person.
across.
Aren't kids like that?
No.
Or like babies?
Yeah.
Potentially, but also like some adults achieve that kind of perception of the world as a result of practice.
There are some rarefied stories online of people as adults saying that they suddenly had a realization, they suddenly became conscious. Who knows if these are true, but there are some people online that say that, like, when they were in college, they suddenly realized that they were actually a thing that existed, and it changed their life. There's a few of these stories online.
Yeah, so where I go with this is that, like when discussion of consciousness usually miss one of the longest continuous traditions that tries to understand the nature of consciousness, which is Buddhism. And explicit goal of the practice is dissolution of the fundamental delusion of the separate self. A person who achieves the final goal of the practice effectively perceives a flow of causes and effects without any kind of distinction between himself and the environment. There's just simply, things are being prompted by other things in an infinite chain of causality. That's it. So we might be, it's an interesting perspective to consider, because we might be chasing something that just simply isn't there. It's just a perceptual thing. It's not actually a phenomenon that exists.
So yeah, I think maybe the people who do research on Marco blankets might actually have more things to say about whether what is the boundary between self and environment.
Yeah, if in that theory, basically, if there's no self-awareness, the self-awareness can be different shape, right? It can be different variables. But if there's no such thing, then there's no way to have a market blanket. There has no way to have a self-organized. So you have to, probably there are some single examples that they don't, but then, by nature selection, it's called. That's what I.
But market blanket is a statistical convention. It tells you about the statistical independence of particular set of nodes in the causal graph from something else, and it's not a hard line, right? Like it's a very fuzzy boundary sometimes. We tend to draw them in places where they're very easily visible, but if you really look at this, essentially it's just the causal independence. It's kind of like depending on what kind of time scale on what you're looking at. That causal independence isn't really true as a thing that actually exists. It's simply for the sake of convenience, it's good to separate it from because from the perspective that we're looking at, the analysis allows us to make this distinction between something on one side of the blanket versus the other. Like, you can't separate yourself from an environment.
No, I think market blanket has a physical meaning, which is it's not only maths. It's basically define the internal and outside. And then if you have that definition, it becomes self-awareness already. Does that make sense?
But there's another perspective.
I think that so this is like the debate in like physics, like does temperature exist? You can say that temperature just reduces to the movement of individual atoms, but that's I think overly reductionist, because even if you understood if you only understood the moving atoms, then you wouldn't have an intuitive understanding of temperature, which is actually useful to have.
Well, but to a different kind of system that observes temperature may not be a meaningful thing. It's only that we care about temperature as a virtual variable because to the beings like us, it's important to maintain the temperature. So if somehow you were a being that does not depend on temperature to exist, then you probably wouldn't simply have any notion of temperature, and you might find the other statistical property of a collection of individual molecules in the gas much more fascinating than the average kinetic energy.
Right, but I don't think that the fundamental particles or the atoms are more real than the temperature. Like they're lower on the abstraction scale, but I mean.
And here we ran out of time.
It's real.
We ran out of time, but Christoph has lots of great points. There was some other question?
Sorry, just a very new idea for me to define consciousness related to embodiment. So you of course would like to do it in a real physical space with robots and everything, but technically speaking, we can make a simulation. So if you're talking about a kid, ball falling down, ball bouncing back, glass doesn't fall, glass doesn't bounce back. These kind of things can be simulated, so not necessarily have to be an actual physical robot. Of course, it will be a subset of reality. Or you can move to other places which are not physical, so you can define different kind of simulators. Can you generate different kind of consciousness in that sense?
So I think this touches on a point that I really wanted to bring up in the paper, which is that if you talk to people about what systems are conscious, is there a boundary for consciousness? Actually, a lot of people might put things on a spectrum. So you might say, oh, rock, that's not conscious, but a monkey seems like it is pretty conscious. Maybe not as conscious as a human. Maybe a cat or a dog is like kind of conscious, and then it becomes a sort of spectrum. So our sort of answer to that sort of thing is that we'd say that people seem to say there's a spectrum of consciousness, and then we tend to say that things living or embodied in a more complex environment correlate that with a high degree of consciousness. So this is our sort of solution to like, okay, well, if we have these theories of conscious function, indicator properties, etc., you implement them. According to that, the system you've implemented is conscious, right? That's the way that it goes. But if it's just in a grid world, right, does that seem conscious to a human? It seems a little bit off, right? But if you had all those systems implemented on a real robot, right, that's inhabiting the real world, then it starts looking a lot more like consciousness for a human. If you had it inhabiting a simulator, which has quite a lot of aspects, probably sits in between. So I think that's the sort of answer we have for these things is, we say, okay, a lot of people have intuition is a sort of degree, a spectrum of consciousness, and the sort of richness of the experience and complexity of the world is, what determines that if these systems have these properties, then they lie along the spectrum according to that.
Okay, we'll close with Greg's question. So here, why we do organize these once in a while? So for now, we've been doing them invite only, and now this is the first one where it's been open to public, and we'll do more if time allows, and we'll find more help to organize. So why we do it is to put very interesting people together and then discuss. Unfortunately, we don't have as much time, but please talk among each other for half an hour. Hopefully they will not kick us out. If not, we also have a Discord channel where we'll continue discussing these topics. So I'll share the slides there, and I'll share the link to that Discord server by email with everybody who joined. So yeah, thanks a lot for joining, and thanks a lot to the speakers and to Wayne to facilitate, and the AI Industry Forum that's helping a lot with the organizations, and the Industry Foundation that renamed it. Yeah, thanks a lot.
Sorry, why would we be